This lesson is about solving rational equations. Before we can do that, we have to talk about what it actually means to solve. So to solve means to find the value of the variable that makes the equation true. There may be more than one value that you have to find, but that just means what value of x are we looking for to make that statement true. So let's look at the simplest type of example to start with so that we can kind of go from there and build off of that to look at more complex functions. So 1/3 equals 5 over x. That's a rational equation because we have two rational expressions on either side that we are being asked to solve for the variable. So a couple different things that we could do to answer this question about what is this actually asking us. So one way to look at it is just to look at it the way you would in grade 9. What value of x makes that true? So proportionally 1/3 is the same thing as 5 over some unknown number. Another way to look at that though is to look at this graph of 5 over x and to interpret this as meaning where is this graph at a value of 1/3? Okay, so a few different ways to kind of look at that problem. And now that we're in grade 12, we're kind of looking at it that graphical way. So 5 over x, just to like get a quick sketch of what that would look like, we know that it's undefined at x equals 0. So we know that we have an asymptote there. And because the degree on the bottom is higher than the degree on the top, this is degree 0, right? There's no x term there. And this is degree 1. Then we know that we have a horizontal asymptote at y equals 0. Okay, so we have our two asymptotes here. And then the fact that there's a 5 on top instead of a 1 just means that we have like a vertical stretch happening. So our function looks something like this. Okay, so when we're being asked, when is 5 over x equal to 1/3? That could be asking us this question. So if this is a value of 1/3 for y, our question is, when does this occur? Okay, so like for what value of x is that graph equal to that value? Okay, so I know that this is a really simple example and you know how to solve it, so let's do exactly that. Let's use the information that you know to be able to solve this. So I'm going to draw it out a little bit just so that we can make comparisons to more complex functions later. So in grade 9, you might have learned lots of different ways to solve this, but the way that I'm going to draw attention to right now is by multiplying by the lowest common denominators. Because you know that when you have fractions, you can only kind of work with them when they are describing an amount of the same amount of parts, okay? So in this case, the lowest common denominator would be anything that goes evenly into 3 and x. So that obviously has to be 3x. So if we multiply by 3x on this side and we multiply by 3x on this side, we're allowed to do that because we're treating both sides of the equation equally. And so now from here what we do is we simplify. So we have a 3 divided by 3 that those divide out, and then we have an x divided by x and those divide out. So we're left with this expression, x times 1, which is just x, over 5 times 3, which is just 15. And this is super nice because not only have we solved the equation in one step, but we've taken an equation that had fractions in it, and we turned it into an equation that has no fractions. Well, I mean, I shouldn't say there are no fractions. Technically, x and 15 are both fractions, but let's just call it polynomial because that's really what it's actually called. Okay, so we have a nice polynomial equation there. We have no denominators that we need to worry about. All of our denominators are 1, so things are good. This is like the big idea of what we're looking for. Okay, so graphically, the question is asking us where is that graph equal to that value, or later on, we'll look at where does one graph equal another graph. And algebraically, we're going to do this kind of strategy of multiplying by the lowest common denominator, okay, the LCD. And that's the goal of that is to obtain a polynomial equation at the end that's easier to solve. We're happy once we obtain a polynomial equation because we can deal with that. Awesome. Okay, so let's move on. Okay. So here we have 4x minus 1 over x minus 5 equals 0. So again, we'll start by addressing this question. What is this question even really asking us to do? Well, one way to look at it is algebraically, what values make this equation equal, or the expression on the left equal to 0. But graphically, it's asking us, where is this graph? Like if we're looking at this as a function, 4x minus 1 over x minus 5, where does it have its zeros? Right? That's really what that means. It's just saying what does that graph look like? Where is it equal to 0? Because that's the y, where the y value is 0, right? So we're wondering where along this line do we have values on our graph? Okay, so let's address it the exact way that we just talked about algebraically. So we have 4x minus 1 over x minus 5 equals 0. So the first thing I'm going to do is I'm going to multiply by the common denominator. So this 0 has a denominator of 1, so I'm going to multiply both sides by x minus 5 times 1, which is really just x minus 5, right? All right. So now I can see that I have some common factors I can cancel out. That will always happen. That's why you chose it. So I'm left with a 4x minus 1 on this side, and 0 times x minus 5 on that other side leaves me with just 0. So now we have a polynomial. And we're really happy about that because we know how to solve polynomial equations. This is just a linear one, so it's super easy. I'm just going to add 1 on both sides, and then I'm going to divide by 4 on both sides. Awesome. So we have x equals 1 over 4. So that means on this graph, this function, 4x minus 1 over x minus 5, would have its x-intercept at 1/4. Now I know, again, super easy example to start with, and that's okay. I just want to look at it on Desmos real quick, just to really hammer that home so everybody's really on the same page. 4x minus 1 over, I forget what it was, x minus 5. Okay, so that graph looks like this. Beautiful. And then we can see that it's equal to x at 1/4, 0.25. Cool. So we can see that our answer is correct, just graphically. Okay, because that's what this question was asking. It says, where is this graph equal to 0? Cool. I could even put y equals 0 as my equation there, and then find the place where those two functions meet. Y equals 0, that horizontal line, and 4x minus 1, that rational function. And then we can see that they have a point of intersection at 0.25. Cool. All right, let's keep ramping it up. So here we have a slightly more complicated equation. X plus 2 over x minus 1 equals 2x minus 3 over x plus 4. Now what is this asking? Again, we'll start there. So again, algebraically, it's asking what values of x would make this equation balanced. Would the value of the left side equal the value of the right side? Totally. It's also asking where this function, so if we have like the left-sided function of x plus 2 over x minus 1, where is that equal to the right-sided function? So where is this equal to 2x minus 3 over x plus 4? So we're talking about point of intersection. That's really kind of what this is asking us about. Another way to frame this question is to rephrase it and change it like this. So if we had x plus 2 over x minus 1, and then we subtract this term from both sides. So we subtract 2x minus 3 over x plus 4 from both sides. Then it'll end up on this side, and then we'll have 0 on that side. Okay, so all we've done is we've effectively moved that term from the right side over onto the left side with us. Now this is kind of reframing the question. Now we're kind of asking, where does this new function, so I'm going to call it h of x, where does it have its zeros? That's what it's asking. Okay, oops, sorry. So I just want to point out that the solutions for this problem and the solutions for this just straight up algebraic problem and the solutions to this related graphical problem, these all have the same solutions, okay? Wherever the value of x is for any one of these, it's going to be the same for all three of them, okay? So we can frame this any of those ways. It's just really important to talk about those differences. So let's, this time, should I start with the graph? Let's look at the graph at the end and let's tackle it algebraically, and then we can kind of compare all of that at the end. So we have x plus 2 over x minus 1 equals 2x minus 3 over x plus 4. Now, just like all the other times, I'm going to start by multiplying by my lowest common denominator. So now that I have more complicated expressions on both sides, that lowest common denominator is going to just be the two denominators together, just like if I go back to that first super easy example. The two denominators together were 3 and x, so I multiplied by 3x on both sides, and it got rid of the fraction on both sides. Okay, over here, multiplying by x minus 5 times 1 on both sides got rid of the fraction on both sides. So you want to multiply by the denominators from both sides like this. Okay, so if we multiply by x minus 1 and by x plus 4 on this side, and we multiply by x minus 1 and x plus 4 on this side, effectively what we do is we're going to deal with getting rid of the fractions on both sides at the same time. So the x plus 4 and the x plus 4 on that side cancel out, and then the x minus 1 and the x minus 1 on this side cancel out. And we're left with x plus 4 times x plus 2 equals 2x minus 3 times x plus 1. And I know some of you are thinking like, Miss, why did you do that? Why didn't you just cross multiply? And 100%, I totally could just cross multiply. The only reason I'm kind of calling it the lowest common denominator, I'm doing that extra step of multiplying by both factors on both sides, is so that we can use this same strategy all the time and not have to adjust it when we deal with inequalities very soon, okay? So just heads up. Okay, so here we are, polynomial expression, woohoo! We are like so happy about that, okay? Because now it's just a quadratic on both sides. Like we totally have skills to be able to solve this question now. So we can just expand and simplify. So we have x squared plus 6x plus 8 on the left. And then we have 2x squared minus 2x minus 3x is minus 5x. And then plus 3 on this side. Bring all the terms over to one side. That's because that's how we solve a quadratic equation, or in general, like really any polynomial equation. And so we have 2x minus x squared is now x squared, sorry, 2x squared minus x squared. And then negative 5x minus 6x gives us negative 11x. And then 3 minus 8 gives us negative 5. Now, again, really simple to solve this equation. We can solve by factoring. Hopefully, now we can't. We can't solve by factoring. That's okay. But we can solve with quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Oops. Oh, that was weird. Is equal to x in this situation. Let me just make sure I didn't make any silly mistakes there. Minus 2 minus 3 is minus 5 plus 3. Yeah, I think we're good. Okay. So now we solve, or we plug in all the values. So we have 11 plus or minus the square root of negative 11 squared. Notice that I put the negative 11 in brackets. You have to do that. All over 2 times 1. Just being really thorough and even putting out in all my ones. Okay, so 11 squared is 121. This is going to be plus 20 over 2. 141 over 2. Let me bring up my calculator. Some ugly number. So this is approximate now, so I'm using my approximation sign. Okay, so then we have two values. We have that x could be the positive version of that square root or the negative. Okay, so 11 plus the square root. Oh, I wonder if I can do that. 41. Oh, I know, I'll just put in brackets. No, can I? Oh, goodness. Okay, cool. And then I'll take that and I'll plus 11. And I'll divide by 2. So I get 11.44-ish over here. And then if I take the square root of 141 and I make it negative, okay, well, I'll do minus, oh man, I wish this calculator was a little bit better. It's kind of lame to work with. All right, I guess I just have to work my rounded value. Darn, I guess that's totally fine. I just really like to use the exact answer until my very last step. But I can let it go for today. Okay, so we have like approximate values for x on both sides. Okay, so now let's just look at the graph and see if we kind of still agree with the work that we got there. So I'm going to close the calculator and open up Desmos at the same time as my note here. Okay, so our question was this. This is the way that we dealt with it, is we looked at when is x plus 2 over x minus 1, when is that function equal to 2x minus 3 over x plus 4. Cool. So we were basically looking at the points of intersection, right? This was like the first way to frame it, okay? To think of this as being one function, think of this as being another function, and then to be asking ourselves, where do those two functions meet? Okay, so if we zoom out, we can see like, okay, they appear to meet in two places, right? Because we have an asymptote over here that they both seem to be approaching. So we have one value here. That's at negative 4.4-ish. Cool. That's what this rounded one kind of looks like. Oh, I should put my approximation sign. And then over here we have 11.44 as well. So cool, we got the right answers. Really nice. Okay, so this question is like done. You know, we've solved the problem. We found the two values of x that make this statement true. Oh, I should actually be so good, and I should also say whenever at the beginning, the very first thing I do is I should say where these functions don't exist. So I should say solutions cannot be 1 or negative 4. I have to start there, and then I have to compare to that at the end and make sure that I don't have any answers that are actually part of my restrictions. So this time we're good because our answers aren't either of those two restrictions, so they're both valid answers, and we have like a good kind of solution to our problem. Now, I know this may seem like a lot of unnecessary work, but this is really important for me to address, is this problem that we just solved by looking at as the point of intersection between two graphs. I'm now going to solve the exact same problem this way, okay? By instead asking ourselves, where is this new function equal to 0? Okay, so you'll see how similar those two functions, or those two kind of solutions are very soon, and you'll be able to see it because they'll be next to each other like this. So again, I'm going to start by multiplying by the lowest common denominator. Okay, that's kind of where I'm always going to begin after I state my restrictions and factor and stuff. So still here, this is like a denominator of 1. So my lowest common denominator is x minus 1 and x plus 4. So I'm going to multiply by that on both sides. Now notice that on the right, of course, I'm left with 0. And on the left, I have both of these terms need to be multiplied by the x minus 1 and the x plus 4. So in the first expression, the x minus 1 and the x minus 1 cancel out, and I'm left with x plus 4 times x plus 2. And in the second expression, the x plus 4 and the x plus 4 cancel out, and I'm left with x minus 1 times 2x minus 3. Now, I just want to point out that again, the goal of multiplying by the lowest common denominator for all the terms is to obtain a polynomial equation, okay? Because a polynomial equation is one that we have strategies to solve, so that's what we want to deal with algebraically. So now I also want to point out the similarities between this first step that we just got to And this first step over here, so notice it's the same, right? Like this is like totally the same thing. It's just that here, if we took this term and we subtracted it on both sides, it would end up on the left side as well, and it would look like this, and we'd be left with 0 on the right-hand side. Notice that obtaining 0 on one side, we did do in that first method as well, right? Like we still got to that place where we had 0 on one side. Here we're just getting there earlier. The reason I point this out is that when we solve inequalities, you actually have to do this step first. You have to move everything over to one side. And we'll talk about why in the next lesson. But for now, just like I really want to point out that I know you just want to cross multiply on both sides, and that's really cool. But actually bringing everything to one side first and making 0 on the other side is a really good strategy because it won't change. Like you can keep doing that all the time, no matter whether you're solving an equation or an inequality. So now, I don't think I need to go any further with this solution because algebraically, this is going to be the same thing as this. Like I'm still, like when I expand and simplify both of these binomial multiplications over here, I'm going to get the same thing. I'm just going to get it on this side. It's just going to be, it's going to be the opposite sign, but the idea is going to be the same just because it's on the other side. I'm going to have all these terms together, and then I'm going to have 0 on the other side. I'm going to get the same answers when I solve, okay? So I'm still going to get x is equal to approximately 11.44 or negative 0.44. So I'm still going to get those answers. Cool. All right. So now, again, let's like compare those things algebraically. So this was the first two, like those two sides of our equation originally. Now I'm just going to change the way that this is framed. And I'm going to turn those off just for a second. And I'm going to type this in as the second way we've looked at the x plus 2 over x minus 1 minus 2x minus 3 over x plus 4. Okay, so now you can see how different this looks from the way that we framed this problem before, right? So here we have this just one function because I have only the left side of my equation, right? Like I've moved everything over to one side. I've created a new rational function that's a combination of these two guys, and I've created this new function. And now I'm asking, where is this function equal to 0, which is a different question than what we asked before, where last time we looked at this as two separate functions and we asked where are those two functions equal to each other. So totally different way of framing the problem, but notice that we got those two answers. And now if I frame it this way and move everything over to one side, and I want to know where it's equal to 0, that's here. Whoa, 11.44, same thing as what we got before. And negative 0.44, which is again the same thing as before. So we can see that no matter how we frame this problem, whether we look at it as two separate functions and ask ourselves where do they meet, or whether we look at it as one big new function that we've created by moving all the terms over to one side, where is that equal to 0? We get the same solutions, okay? So two different ways to kind of frame this problem, but algebraically we get the same result, okay? Okay, I'm going to stop this video here because this is kind of the big nuts and bolts, and then I'm going to continue on with a couple more examples and then some problems that kind of carry on.